I think we should start because we have a schedule, otherwise we make a delay along the line. So, okay, so it's a great pleasure for me to introduce Joseph, who is, I think he's just coming straight from the Midas meeting. And you know, Joseph is an infectious disease modeler, and he's directing the modeling section of the Hong Kong University School of Public Health. He's an expert in influenza. And you know, for some of you that, you know, from time to time my students ask me, well, you know, but we are a PhD in network science, a PhD in physics, etc., etc. Well, actually, you know, Joseph has an operation research, a PhD in operation research from MIT, and a BS in chemical engineering. So you see that, you know, the career trajectories are very, you know, circuitous, and he is now in public health. He's also a member of the Center for Communicable Disease Dynamics, that is one of the Center of Excellence of the Midas group with Mark Lipsitch. He's advising the WHO, the UK, etc., etc. So it's a true pleasure to have him here, and he will talk about the underlying global spread of epidemics, something that many of us resonate with. So,
thanks, Alex. Thanks for coming, everyone. It's a pleasure to be here. So I'm going to present this work, which is joint collaboration with my postdoc, Dr. Ling Wang, and it was just published in January. So if you're interested in seeing the details, you can find the paper online. So today's talk is going to be a bit more easier for me than usual because I'm speaking to a specialized audience. All of you are very familiar with GLIM and global simulation of epidemics. So this is just to illustrate the complexity of global spread simulation since people first used it in the late 70s, early 80s. So the most cited early work was work by Aaron Longini, who started doing this in the 1980s, and at that time, the metapopulation model has about 55 populations, so relatively small compared to zooming to the most recent work, which is GLIM, the state of the art, has on the order of 3,000, 4,000 populations, modeling basically the entire global human mobility via air travel. And in this figure, we also put the major emerging infectious disease events that either have been reading in the literature, historical events, or headlines most recently in the past few years. So for example, in just the past 7 to 8 years, we have Ebola, we have MERS, we have 2009 pandemic, and of course last year we had Zika. And during all those events, global simulation of epidemics has been a major tool for studying how fast or how likely the disease is going to be spreading from the origin to other parts of the world. So this has been basically the mainstream methodology for studying how infectious disease spread around the globe through air travel. I'm going to skip this because you all know what metapopulation model is, especially in the global spread setting. Of course, all of you are familiar with it because this is the tool that you guys are developing, so I'm going to skip that also. Okay, I think most of you, or even all of you, are familiar with this paper published in 2013 by Brookman and Helbing, which looks at sort of semi-analytic approach of on the problem about how do we explain how disease spread from the origin to other parts of the world using some analytical approach. So not just simulating, but trying to make a statement or getting some insights into how does the spread relate to the epi parameters and also the network properties. So the major insights that they obtained in this study is that, well, first they introduced a measure of distance for the air travel network. That's what they call the effective distance, which is related to the flow, air traffic between any two populations. So it's basically proportional, the distance is proportional to the negative of the log of the travel flux between the two cities, meaning that the higher the flux, the shorter the distance. That makes sense intuitively, but it wasn't clear why they chose this particular functional form, and the distance has to be related to the log of the flux. It just so happened that it worked in their paper, in their studies. And second, which is the most important finding in this paper, is that instead of looking at the entire network, how things spread in the entire network, they took a reduction approach first, looking at, say you pick an origin, that's where the disease first emerged, and then you form the shortest path network of the entire network, using the distance metric that they introduced, the effective distance. And they show that the spread of the disease in this shortest path tree network, which you can call SPT network, is basically very similar to how things spread in the original complete network. In other words, how things spread in the entire network is pretty much driven by the structure of the SPT network. So that's a very interesting finding. And also, what they showed was that the epidemic arrival time at different parts of the world is linearly related to the distance between those two places, the origin and the destination. But not analytically, mostly just making statistical association from their simulation findings. So our objective in this study was to look at it from an analytical point of view and build on what they have done here to try to make a statement on. So instead of using simulation and say that these things are sort of related in this way, how does that happen? Can you start from first principles, the structure of the basic metapopulation model, and then recover this relationship. So that study was published in 2013, but there have actually been a couple of studies looking at similar problems, but in a much more analytical, using a much more analytical approach, and not at a global scale, at a smaller scale. So this was a study by Vitro et al., which was actually published quite a bit earlier, 2008, but for some reason it wasn't cited by the previous paper, so it took some time for me to dig this out. But this was very important for the problem that they were looking at, which is, say, if you start with two populations, okay, origin, and then say a population that is strongly connected, okay, to the origin through their travel. What they show is that, well, under some approximation, the expected arrival time could be derived analytically, shown in this formula here. So TA here is the epidemic arrival time at the downstream population, and it could be explicitly related to the growth rate of the epidemic, which is lambda here, and also the flux between the two populations, Fij here. So this is an explicit analytical expression relating the epidemic arrival time to the epi parameter, which is the growth rate, and the network parameter, which is the flux between the two cities. But this is only an approximation, because the approximation, the assumptions that they made for when they develop these formulas may not necessarily hold in all occasions. In particular, there were some major shortcomings of their approach. The first is that the PDF from this approximation doesn't integrate to one, so that's a major problem. If you talk to statisticians or probabilistic people, they would view this as a sin, if not a crime. So that's something that needs to be rectified. Second, the theory becomes inaccurate when seeding is continuous, meaning that in the previous setting, okay, when they were just looking at two populations strongly connected by air travel, seeding was just in a singleton event. Okay, so 10 infected seeds at time 0, and then let it go. But you can imagine that as things spread around the world, okay, if you look at more downstream populations, say I'm 2 degrees away from the origin, then the seeding for these populations are not going to be a single effect because importation will still be coming in from all edges. So what they show in this paper is that when that happens, okay, if they go beyond the first degree of separation, then the theory starts to break down. Okay? And the further you go, the more degree of separation that you look at, the more inaccurate the theory becomes. So that's the second thing that we need to rectify if we were to try to get a more general theory of what they've done here. And then third, the theory also becomes inaccurate when there's a hub, meaning that, so in this work, they look at pretty simple structure, basically just a single, all populations are connected to the origin through one path. Okay? And the origin is the only possible hub in their paper. The hub would mean they have many connections, and each connection has significant flux. So what they show here is that, well, if the origin, for example, is a hub, then the theory also becomes inaccurate. So these are the three things that at least we have to address if we were to improve over the previous two studies. So a little bit about our experience in this global metapopulations analysis. We first started doing this in 2007 to 8, okay? But not from an analytical perspective. We were trying to address the question that, so it was 2007, 2008. There were two things that were bothering people at that time. The first is the potential occurrence of a flu pandemic. So it was 4 to 5 years after SARS, and pandemic flu was much concerned, not just in Asia, but also in the States. As you might remember, President Bush at that time invested a large sum of money on pandemic preparedness. In particular, there was a large investment on Tamiflu stockpile, which is still happening today. So I think even today, the stockpile size is enough to treat about 25% of the entire US population. So they have enough Tamiflu to treat 1/4 of the entire population. So that was, I think, the stockpile size back in 2007 is similar to the stockpile size today. So that's the first thing that people were worried about. The second thing that people were worried about at that time was that there was substantial Tamiflu resistance emerging in seasonal flu strains. It was thought to be impossible before 2007 because all the Tamiflu resistant strains that people have identified, they all suffered from substantial fitness scores, which means that yes, resistance can emerge, especially in treated people, but if they emerge, they cannot spread to other people compared to the wild type. So they will always be outcompeted by the wild type because of the fitness scores. The emergence of the Tamiflu resistance H1N1 strain, season 3, changed that paradigm completely because first it emerged, and then second, it outcompetes the wild type within 12 months and became the dominant seasonal flu H1 type. Okay, so these two things completely changed how people think about resistance. Now, if you put the two together, we have invested a lot of money in Tamiflu or pandemic. We hope that that will be one of our most effective weapons for treating or stopping the spread of pandemic flu if it happens. Second, we thought resistance used to be impossible to be outcompeting wild type, but now that's not the case because there's a natural phenomenon showing you that the resistance rate can be more fit to compared to the wild type. So that's why in this work we start asking the question, in that occasion, is there some strategies, is there something that we can do to basically minimize the risk that if resistance emerge, your Tamiflu stockpile will be completely ineffective. So that's a long story. And to address that question, one of the things that we have to do is to build a metapopulation model, global model, to show that if resistance strain emerge in one part of the world, how it might spread to other parts of the world, and what are the strategies that we can do to minimize that impact. And that's actually the work that, through that work, I first connected to school. It was, I think you guys were still in ISI at that time, or affiliated with ISI at that time. And there was a meeting, and this was the first time I presented my research to us school. So that was the my starting point of working on this kind of problems, global simulation of epidemic spread. And since then, we have extended the model to include more cities. So we acquired data from OAG, the air travel data from OAG, and then the demographic, the world population data from Columbia University. I think that is a freely accessible data set, but the OAG one you have to pay for it. So we have the experience and capacity to do global simulation of epidemic spread. And again, the objective of this study is to analytically characterize how epidemic arrival times of different populations in the world depend on two things: the epi parameters, and also the network features of the air travel network. So again, because you are very familiar with GLIM, these should be very well-known statistics to you. That typically these kind of simulations have about 2, 3, or even 4,000 populations, depending on how you define, the global populations and assign them to be connected to different areas. This is the histogram for the mobility rate in the networks that we built, which I think is similar to the air travel network underlying GLIM. Maybe not exactly the same because different ways of dividing the world, but in terms of the summary statistics, they are similar. So x-axis here is mobility rate, which is defined as the average daily travel volume divided by the population size of the origin. So meaning, on average, each day, what percentage of the origin population is traveling outside. So
here, Joseph, are you using the origin destination flows, or you're using the, I would say, the seats volume between destination?
So this is Fij in the Approximation paper. So on average, how many people are traveling from Rj, and the denominator is the population.
Yeah. But this traveling flow is an origin destination, so it's really, because you can calculate how many people travel from New York to Paris, but then they go to another destination. So these are origin, destination, final. So
the data that we get from OAG is booking data.
Or these are the booking data,
right?
Okay.
So excluding the transit.
Yeah.
So these are not seats data. We are not counting the number of seats available on airplanes. We are counting the number of bookings actually made. So yeah, as you know, it has a pretty wide range from 10 to the negative 7 to 10 to the negative 3. Okay, so we're going to start with the true approach, which is to start with the toy model, the two population model, okay, connected by an arbitrary flow, Fij. And we made two assumptions, which has been commonly made in similar studies. So, of course, we are not the first one to study this kind of problems, and we have seen people making these assumptions in other studies. So, but they didn't state it explicitly. Okay? It was implicitly made under the assumptions that they were doing, they were using in their calculations. So we make it explicit. Two assumptions. First, the expectation of infections from J to K, any J to K, is a non-homogeneous Poisson process with intensity function Wjk, which is the mobility rate, times the prevalence of the disease in the origin. Okay, so if you think about it, the prevalence will be proportionally affecting how fast how many infections are being exported. Okay, so if the assumption here is that each person in the origin population has equal chance of traveling from J to K, no matter what their disease state is. So this should be intuitive. Second, which is the most important one, the first few expectations occur while disease prevalence is still growing exponentially. And the NPP intensity function in this case would become this thing here. So basically replacing the disease prevalence in assumption 1 with the exponential growth. Okay. So how does that help? So even with just one, we can express the PDF in terms of the intensity function very easily, as we know. And with assumption 2, that if you work out the calculations, then the PDF can actually be expressed in closed form, which is shown here in equation 1. Okay, so this is a PDF that explicitly relates the epidemic parameters, which is the growth rate and the seed size, Sj, and the network parameters, which is Wjk here, to the epidemic arrival time, okay, which is the random variable that we're looking at. So the next question is then, you have an expression, but how good is the approximation? Because these are assumptions, okay, and this is obtained under these assumptions. So we compare the PDF in equation 1 with the simulated PDF from the simulation under a broad range of scenarios. But first, let's just look at one particular example. Suppose the epidemic doubling time is 6 days, and the generation time is around 3.5 days, which is similar to flu, epidemic flu. A, B, C here. A is looking at the first expectation, so the epidemic arrival time. The red dash curve is showing the PDF from equation 1. The simulated PDF is shown in gray here, and we're looking at 3 levels of mobility rate, ranging from 10 to the -4 to 10 to the -6, which is well within the range of the mobility rate histogram that I just showed you in the previous slide. So as you can see here, they are used very well. It's almost indistinguishable. If you look at the arrival time of the 5th importation, which is shown in the middle here, we see similar result, but then it starts to break down. The accuracy becomes quite significant when you're looking at lower mobility rates, 10 to the -6. That's kind of intuitive if you think about it, because the weaker the mobility rate, the longer it takes for expectation to occur. And the longer it takes for expectation to occur, the growth rate will be less likely to be exponential. You'll be going towards the peak, so it's going to be slowing down. So that's why we see inaccuracy. Actually, the theory, the approximation theory, will predict a faster arrival time because you're assuming exponential growth, but the actual setting is going to be slowing down. C is the 10th expectation. Okay, similar to the 5th expectation. It's working out pretty well until the mobility rate hits the order of 10 to the -6. And the discrepancy is basically generated by the same mechanism for the 5th Okay, so basically, this shows that in this particular example, the approximate PDF works really well, and it integrates to 1, so it fixed one of the problems that I mentioned in the paper. Any questions at this point?
So this is just importation, right? Just not triggering local outbreak. So it's not like is it the fifth is the fifth importation or
The 5th importation, the 5th seeds arriving from the origin.
from the so it doesn't have anything to do with like triggering like local outbreaks. It's not because our routes are
We're just looking at the importations from the origin. Okay. So next is to run many different scenarios and to see whether this analytical framework will break down at some point. So still 2 population models, but vary the parameters, the underlying parameters within reasonable range. So generate 100 different scenarios using 11 sampling within the space. So epi doubling time between 3 and 30 days worldwide for the kind of EIDs that we have been looking at, ranging from epidemic to Ebola. Seed size between 1 and 100. So seed size is how many infected people used to stop the epidemic from the origin. Mobility rate ranging from 10 to the -6 to 10 to the -3. Again, well within the range that we see in the air traffic network. And population size of the 2 cities ranging from 1 mil to 10 mil. Okay, typical metropolitans. For each of these 100 scenarios, we simulate the PDF using 10,000 stochastic realizations. And we look at the QQ plot of the simulated PDF versus the analytical PDF that we get from the framework. So x-axis is the analytical PDF from our framework, and y-axis is the simulated PDF. So these are QQ plots, which means that if you see that the data lies along the diagonal, it means the PDF are the same. Any deviation from the diagonal indicates discrepancy between the analytical and the simulated PDF. Okay. The order are the same as before. First expectation, 5th expectation, 10th expectation. So what we see here is that for the first expectation, which is the epidemiological type, basically they all lie along the diagonal for all 100 scenarios. You start seeing some deviation in the 5th and 10th expectation for the same reason that we have talked about in the previous slide. If you look at the average, so not looking at the PDF, but just look at some of the statistics, the mean time of arrival, then the percent error for the first expectation is well below 1%. On the order of 1 to 2% for the 5th expectation, and a little bit, a couple of percentages more for the 10th expectation.
Sorry, this one is the yellow and the blue, so the yellow is...
The yellow corresponds to scenarios where there might not be an expectation by the time that the epidemic has finished in the origin. So in some scenarios, okay, you can actually calculate probability that there will be no expectation to the downstream population just because there wasn't enough infections in the origin to do that. Okay? This is just to show that even under those scenarios, if you condition on there is an arrival, so a conditional PDF, conditional on their expectation, then the framework still works. Okay. So yellow means there's some chance, but even those yellow dots, the chance is very small, like 1 in 100 or 1 in 1,000. Okay, so next we are going to address the second problem that I've mentioned about the control paper, which is what do you have to do to adjust for the hub effect? Okay, so remember they said that their framework starts to break down if we are looking at a hub, if the origin is a hub. Okay, so so this time we are not just looking at a two-population model, we are looking at more downstream populations, but still just 1 degree of separation, just 1 edge beyond the origin. So the origin could be connected to a number of downstream populations. So if you were to write down the differential equations, treating this as a deterministic spread, and then assume exponential growth, just like the assumption that we made of one of our core assumptions, then the change, the differential equations for the disease prevalence in the origin is simply this thing here, right? It's equal to the growth rate times the prevalence, because it's growing exponentially, minus the outflow of infected people to the downstream populations who travel. If you rearrange, okay, if you just pick one particular downstream populations and focus on, let's say J here, okay? Let's rewrite the equation this way, singling population J out here. So Wij times II here is the intensity function for the NPP expectation process of J. Okay, I'm focusing on this link here. If you do that, what you see here is that in that setting, you can actually argue that the growth rate has sort of have been adjusted. Okay, if you discount, if you're just looking at this process, you have to discount the original growth rate by the summation of the mobility rates to the other populations. In other words, if I'm just looking at when would the first expectation occur in population J, okay, before that happens, before that expectation happens, from the perspective of population J, the disease prevalence in population I is growing exponentially, not at the nominal rate, lambda I, but at the adjusted rate, lambda I minus all the mobility rates. So that means that the NPP for this, the intensity function for that NPP here, you have to adjust the growth rate in the origin population by this. Okay? And if you do that, this is what will happen. So we're now moving on to a more realistic network, looking at the WAN-SPT, the shortest path tree network that Brockman proposed it, but using the distance, using the data that we have in our study. So build this network, SPT, and using the same scenarios that are generated before, 100, okay, randomly generated scenarios. Let's say we start the epidemic in Hong Kong. This is the summary statistics of the SPT network with Hong Kong as the origin. So here, we show the performance of the framework if we do this effect adjustment. Again, it's a QQ plot. X-axis is the analytical PDF from our framework. Y-axis is the simulated PDF from the simulation. Red corresponds to if we haven't done any adjustments.
Okay. So, but this is a tree. This is not kind of like a star control. So it's the shortest distance from the Brockman's calculation. If you pick a region and then you calculate the shortest distance, it give you a tree structure. It's not a star structure. How do you account for like a true hub?
So the roots of the tree is the epidemic origin.
Okay.
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 And we are looking at the first.
Oh, only the first.
Oh, at the moment we are looking at
the
first. Okay, so at this point it is a star.
Okay.
So this is the D1, what I call D1 population. Populations that are 1 degree of separation from the origin. Just you can get to it through one edge. So red is without adjustment. Blue is with the adjustment that I mentioned. So what you see here is that with the adjustment, all the points are pretty close to the diagonal. So suggesting that the analytical framework is a good approximation under all the scenarios that we looked at. If we look at the percent error in the mean epidemic arrival time, then it's around 1 to 2%. Okay? Performance slightly worse than the toy model because now we have more complexity because we have an extra approximation, the Hop effect adjustment. Okay, so I think we think that takes care of the Hop effect. Next, the last thing that we address is the continuous seeding. Okay. If we look at a path connecting the origin to a population J, and then there's another population K connected to J, so the linear network IJK. Just like what I'm showing here, suppose we focus on the preference of population J, the middle population. This is the time of first arrival, so this is when epidemic will start in population J. J is subject to continuous seeding, so that will affect the implantation time, the epidemic arrival time of K. In order to figure out how that would affect the epidemic arrival time of K, you can look at this figure. So basically, the main message here is that after the first arrival, the subsequent arrival in population J will each generate an exponentially growing infection tree under our assumption. Okay. So the process that affects the epidemic arrival time of K is not just one single exponential, but a linear combination of exponential growth. But some will grow earlier than the others, depending on how soon implantation occurs in population J. Okay. Long story short, we can work out the math. Okay. And then, if we make this assumption here, which is based on the two population model, and the assumption is that conditional on the first arrival in population J, which is this time here, the subsequent inter-arrival times will be almost deterministic, which means you can approximate them quite well using just the expectation, which can be calculated analytically from our previous equations for the two population models. Okay, if we want to know the details, we can take a look at our paper. But this is the result. Okay, conditional on the first arrival. Okay, the subsequent arrival time in population J. This expectation is simply this expression here. A little bit messy, but still analytical. So that itself is, I think, a minor insight. It means that all the stochasticity in the arrival times is generated mostly by how soon the first arrival occurs, which kind of makes sense because this gives you information on how much preference there are in the origin population. Okay, so if we do that and then calculate the analytical PDF, then we see that the framework remains pretty accurate, which I'm going to show you in the next slide. But before I do that, I want to introduce this technique, which we call the path reduction. Okay, this is not essential for the analytical framework at this point, but it will be useful when we study how things spread, not just in the SPT, in which case each population is connected to the origin through just one path, but in the actual network when there are multiple paths. Okay, some of them are dependent. So far, what we have talked about is that from I to J, okay, the expectation is a non-homogeneous Poisson process. From J to K, it is also a non-homogeneous Poisson process. So then we ask, well, what about I to K? If I don't care about J, if I just want to know how soon things arrive at K, given the starting condition I, what statement can I make? And our hypothesis is that, can it be an MPP? also non-homogeneous Poisson process, which is driven by some seed size, which you probably need to adjust because we've skipped J, so there must be some changes to the parameters. And the answer is through simulation, not analytics. Yes. Okay, meaning that if we calculate the PDF for the epidemic arrival time for K, and then we fit it, we find the best parameters that would fit under the assumption that this process must be an MPP, then it works out pretty well. Okay. So these are the results for the SPT. If we look at populations that are 2 degrees of separation away from the origin, then what you see here pretty much extend to the D2 populations. Again, red is without continuous seeding, but with hub adjustment. Okay, doing hub adjustments, but no adjustment for continuous seeding downstream population. If we do the continuous seeding adjustment, then things go back to the diagram. Okay, average error still on the order of 1 to 2%. If we look at further downstream, degree 3, degree 4, then again it still works. But here I'm already implementing this path reduction thing, okay, not just doing convoluted integration, but using also the path integration. That's a path reduction. So this is the final piece. The entire network. The major difficulty in this problem is that previously in the SPT, okay, unless they are sitting along the same path, otherwise the path connecting two populations from to the origin, they are independent. Okay, so in the SPT, there's only one path connecting each population to the origin. But in the actual network, there could be multiple paths that are dependent. And if we want to calculate the epidemic arrival time for any population, for example here, K, then you need to account for that dependency. We didn't know how to go about doing that, so we made some conjecture, which is the dependence among these paths, okay, all the possibly dependent paths between the origin and origin K, any destination K, would be weak. Okay, weak enough such that we can treat them as independent. And if that's the case, then if you want to calculate the epidemic arrival time at K, then you basically superposition all these paths. Okay? So under this superposition operation, the assumption is that these paths are independent. So as you know, superposition of Poisson process, the intensity function for that is just the summation of the intensity function for its constituent processes. So that's why we made that path reduction approximation. It allows us to collapse all the paths with an intensity function into one single path, for which the intensity function is the summation of its constituents. If we do that, then these are the results. Okay, so here we are again looking at those 100 epidemic scenarios, but the entire network now. Okay. X-axis analytical PDF, y-axis simulated PDF. The D1 populations that are directly connected to the origin are shown in blue here. Yellow is showing the populations that are 2 degrees of separation away from the origin, and red the rest, okay, further away from the network. So here we have around 200 something populations for D1 populations, around 1800 for D2, and then around 200 for the others. So most of the populations in the network are either 1 or 2 degrees of separation away from the origin. And here Hong Kong is the origin, okay, the same as before. So what we see here is that there are now significant deviations from the diagonal, which means in some cases the analytical PDF is not doing so well compared to before, but still not too bad, because if we look at the expectation, the mean epidemic arrival time, then the area is on the order of 4 to 5% on average. This is just the histogram of the data points here, showing that most of the data points is lying along the diagonal. There are deviations, but they are not there of the minority. Okay. So that's all for the analytics. I think we have done, we've made some progress on understanding how global spread of epidemics depends on the epiparameters and also the network parameters quite explicitly. So the next thing that we're trying to do is to think about applications. What can we do with it in the public health setting? So one potential application is for inferring parameters, statistical inference. So inferring epiparameters, for example, from epi data. So we tried to apply this framework to a problem that you guys have looked at before, which is in 2009, the pandemic, when that happened, GLIM was used to estimate the basic reproductive number of pandemic flu, H1, in Mexico. Okay. And I think the approach was to simulate the likelihood using GLIM and then figure out which value of R0 would maximize that likelihood value. Okay. So here we're trying to approach the same problem using our framework. Instead of simulating the likelihood function using the simulator, because in our framework we have an analytical PDF, so you can explicitly write it down. You can write down the likelihood function and then just look at where the maximum occurs. Okay? So one of the advantages that is, of course, much less computationally intensive. So the next question is, will it give you the same answer? Here, x-axis is the epidemic start time in Greater Mexico, which was unknown. So even in the original study, some assumptions was made about the epidemic start time, not in Greater Mexico cities, but in the actual origin. So in your simulation, you started at a more remote part of the world, and then figure out through the local diffusion process, the local commuting processes or regional travel, how long it will take to hit Greater Mexico City, and then through that, how long it will take for it to hit other parts of the world through air travel. So here, because we're not modeling local diffusion, so we seed the epidemic in Greater Mexico City and then consider a range of start dates. So what we see here is that if our assumption on the start date is consistent with the start dates that the assumption that was made in this study, then the estimates are basically the same. The point estimates are at least are the same. The confidence interval is narrower in our study.
So I guess I'm not clear on what you're doing here. So you're starting the outbreak in Mexico City, and then doing what with that start date?
So in this study, the problem was using in the dates of first implantation in different parts of the world, say different parts of US, different parts of Europe, and then infer the basic reproductive number of pandemic flu in Mexico.
Yeah.
So that's the problem.
Yeah. So what are you using to estimate R0 in your study?
The same data, the same methodology. The difference is that the likelihood function in our study is based on our framework, analytical framework, which is analytical. You can write it down.
No, I got that, but their study seeded it in Puebla, and you said you started yours in Mexico City, so it doesn't sound like it's the same data. Or maybe I misunderstood that.
So in the GLIM simulation, it started out in the rural area, and then just let it simulate through local diffusion. And of course, the most likely airport that will be hit will be the one in Greater Mexico City.
Yeah.
So basically, we approximate that by saying that, okay, this is the date when the seeds start in Greater Mexico City, because we're not modeling the more upstream spread process. Is that okay?
Maybe go on. I guess I still don't understand what you're using to estimate the R naught. So you have then the arrival time at all the other cities in the world is what you're using to estimate the R naught.
Yes.
Okay.
Same problem here, but the only difference is that Glenn seed in a rural area in Mexico simulates all the way, but because we don't have that process, we don't have we're only including the major cities metropolitans. So what we have to do is assume the start dates in Mexico City. Okay, so we don't have that more upstream process.
I understand. So February 22nd will be the date that you see the infection in Mexico City, and then you have the arrival time at a whole bunch of other cities in the U.S.
Yes.
And you use that distribution of arrival times with your PDF to estimate the R naught.
Yes.
I understand. Okay.
Yeah, it is shifted by a few days because in Puebla was February 15, I remember something like,
No, yeah, I got it. Thank you.
Okay. So that seems to be useful too in this setting. And it's particularly useful when you're not inferring just one parameter, multiple parameters. Okay, so imagine that if you have multiple parameters, then if you are using the simulation approach, then it means that you're approximating a higher dimensional function using simulations, in which case you need more points, you need more realization. Whereas if you have an analytic framework, okay, unless your parameters are number of parameters is very large, otherwise it still works pretty well when you have 5, 6, or 7, or 8 parameters. So this is our second case study, 2014, Ebola in Liberia. We applied our framework to retrospectively, so this was not done in real time, of course, because we did this in 2017. But looking back at the data, okay, supposedly, if you have the data coming in near real time, you can now cast the total number of Ebola cases. And also, if you have the model, after you have inferred the parameters, okay, you can use it for forecasting. For example, predicting the time for the next case expectation from that region. So the problem setting is similar. We use the arrival time, expectation time of Ebola cases to other parts of the world from Monserrado, and then infer the unknown parameters, which includes the epidemic growth rate, but also, more importantly, the case reporting proportion. So, what are the proportion of actual cases that were reported? In the literature, there was a group from the US CDC using a different approach to do that. Okay? Using a capture-recapture approach, they estimated that around 34% of Ebola cases were reported, okay, in that part of the world during that part of the epidemic. So using our framework, we came up with a similar proportion, okay, accounting for potential changes in reporting rate, because at some point in time during that epidemic, there was substantial increase in healthcare facilities, which allows a higher reporting rate. So again, long story short, what we estimated here is that the reporting proportion was quite similar to what they estimated here with a completely different approach. Okay, so this was based on capture-recapture approach. I think what they did here is that they have two independent surveillance systems, and based on the cases that could be simultaneously identified in both systems. Okay, this is a well-known method in ecology. They could estimate what proportion of cases were actually reported. Okay, so the data that were used to came up with this number is completely different from what we used here. Here it's just using expectation time.
So this is the exportation like internationally to other places.
International.
Also, they know that those cases are from that region.
Yes.
And for the epi data, is it still in kind of like a exponential growth phase? Like when you're doing the kind
So
of
these are observed cases. from the WHO. So this is not necessarily generated by changes of the exponential growth rate. It could be just changes in the reporting rate. And we did try to take into account both, whether there's changes in exponential growth rates and it didn't affect the parameter estimates.
So for which cities are you using the observation of cases?
Expectation or the epi curve?
I guess I'm not really clear at all on what's going on there. So you have the number of Ebola cases in Monserrato, and then the arrival time of what is being used.
The arrival time of cases exported from this area to other parts of the world.
So outside of West Africa.
Outside of course.
Okay. And so what's the intuition for why the confidence intervals are so small given how few exported cases there were?
The confidence interval for this,
For everything.
this is not actually that narrow. So, for example, if I pick this one here, 20% plus or minus 10%, which is a bit wider than what we have here.
But I guess I'm trying to understand, I would call that narrow given that there were only a handful of exported cases. Most of them were healthcare workers that maybe went home and
No, we discounted that. So we are only looking at non-healthcare workers. So one case was, I think, Dallas, US.
right, and so how many total cases would you have used for your estimate then as well?
Total number of infections,
Total number of exported cases from Monserrato was how many?
1 to 2.
So with 1 to 2 cases, you can estimate the reporting rate with that degree of accuracy.
And I think the reason is that the thing is growing exponentially. So even if it's just 1 to 2 cases, if you translate this back to the time that the epidemic has been going on, because the process is growing exponentially, then it sort of like narrow down the time.
So it really is pretty heavily dependent upon the exponential growth that we saw in that part of the operation.
Okay, so this is just to show that, well, first, the booking data is just booking. It doesn't account for cancellation. So when we look at the OAG data, we didn't see a drop in booking in August, which we knew travel restriction was issued by the WHO, and then as a result, people did cancel their flights, their travel to this area. So we didn't see that in the booking data for August. Okay, but when we look at September, the subsequent month, we see that there was a substantial drop in booking compared to a year before. Okay, so comparing the difference of booking in August 2013 to August 2014, okay, that was quite similar. But when we look at the booking volume between September 2013 and September 2014, there was a substantial drop, presumably attributed to the travel restriction issued in August 2014. Okay, but that drop, we didn't see that in the booking data because booking data didn't record cancellation. So what we did here was that suppose we account for such travel reduction and assume that the actual travel volume in August was reduced by the same amount that we observed in September. Then basically the result is consistent with the observed expectation time subsequent.
Can I ask another question?
Sure.
What would be the estimate of the number of exported cases that were missed, given the reporting rate? Does it imply that we missed, there were twice as many exported cases as we actually observed?
Expectation that we have missed. Can you elaborate on that?
So you have the estimated reporting rate of 34% of the cases, right? And so we observed 2 cases that were exported. Would your model be able to make predictions about the number of exported cases that were missed?
But that would be very different. So the reporting rate here is talking about surveillance and reporting behavior in Montserrat. Identification of imported cases will be a completely different scenario because you're looking at, for example, here, how carefully people are monitoring importation of Ebola, which will be very different. The percentage of the probability of detecting Ebola importation will be much higher in the States compared to the reporting proportion in Montserrat. So it's a different question.
I understand, because you're fitting to the number of exported cases. And so really the reporting rate is largely being driven by the fact that it was much more likely that someone from Liberia would have shown up in the UK or somewhere else, not in Dallas. And that the connectivity between, given the low connectivity between...
So let me put it this way. So we assume that all expectations, any expectation, will be identified with probability 1. And the first was identified in Ghana, the second was in Nigeria. Even the Nigeria is sort of borderline expectation because he was symptomatic. He was retrospectively found to be symptomatic by the time that he arrived at the airport for travel, but the travel agent didn't stop that person to get out of that.
Joe, I think the confusion here is probably so is the 30% estimate on the reporting coming from your model or is coming from the paper? No, it's coming from the paper. So you're considering that number and then you correct basically the data according to that.
This is independent, so this is just a comparison.
Yeah.
What I did here was completely independent of what you did here.
So and you are comparing with those results.
I'm just comparing the outcomes.
Okay, so you look at what you got in importation, and from there you can estimate the underreporting.
Yes. So these two are independent. What I use here, the method here, the data here are completely different from what I use here. This is just for comparing the results. Okay, so in conclusion, we developed a framework that relates how epidemics spread around the world with the epi parameters and also the network parameters. In doing so, we came up with a closed-form PDF for the epidemiology type for any 2 directly connected populations. We have made some advancement compared to previous work in terms of the analytics for doing that, including adjusting for top effects, adjusting for continuous seeding, and using a path reduction to do path superposition when we try to calculate the epidemic out of time in the entire domain area. That's all. Thank you for your attention.
Thank you very much. There have been quite a number of questions already, so is there any very urgent question from the audience now? Please go ahead, because otherwise we go into the next. I have just one actual question. So because all this framework is, I would say the analytic part is wonderful and it allows to understand a lot of things. And for me, it's a little bit the application part, because as you were saying, neglecting all the diffusive term that you get from the fact that you have that those metapopulation are adjacent and there is a lot of commuting, infection, etc. So how much do you expect that these things will change, these results will change, and that can explain things where you include the short range diffusion? That is a network as well, in a sense.
So I recently had the idea of using the same framework for modern regional spread. Let's say look at the United States and look at how flu spreads in the United States. So simultaneously considering both air travel and regional flow. And I think the framework might be actually more accurate in one sense, because the higher the flow, the more likely that the assumptions that we make here will be valid, which is expectation will occur when spread is still exponential. So because regional flow tends to be has a high volume than air travel, I think that might work better, might work better because of that. In the other direction, it might not work as well because there are now much more dependency about the different apps. So dependency here, the air traffic network is relatively weak. I'm not so sure about regional spread. So you can go either way. That's the next thing that I try to find out.
Any other question?
I have a number of other questions, but we have time to talk later, so
Yeah.
we can.
Okay, thank you very much.
Thank you.
And you are